Alright guys, sorry about that. I don't know why my video turned off. My camera just shut off right in the middle of what I was talking about for no good reason. So just to pick up what I was briefly saying a few minutes ago, a phase portrait is really just a picture like this that shows me all of the infinitely many solutions to the linear system of differential equations, right? Remember that when we solve x prime equals ax, right, we don't just find one solution, we find a general solution that has C1 and C2 in it. And every time we choose values for C1 and C2, we get one of the curves on this picture. So there's many, many values of C1 and C2, and therefore many, many curves on this picture. And I really want you to think of it like it's a fluid flow that you're looking at. The arrows and the directions are showing the current of the water. And if I was to drop a feather in at a certain point at time 0, this would be like giving you an initial condition. If you had an initial condition to go along with this differential equation, well, then you could put that feather at that spot right at time 0, and then this curve that feather is sitting on tells you as time goes forward where that feather is going to go. Right? So it traces out a curve in this phase plane. Right. In the case where one of the lambdas is positive and one of them is negative, the nature of this phase portrait is it looks like the origin is a saddle point. Right? Because some of the arrows are emanating out from the origin and some of them are coming towards the origin. Right? But another possibility is you could have two lambdas that are both positive, right? Now, if that was to happen, of course, your general solution is going to look like two terms here, right, with a C1 and a C2 in it. But it turns out that no matter what your C1 and C2 are, right, for example, imagine that C1 is 1 and C2 is 0. Right? So then you would get exactly this curve right here, right? Well, whatever this vector is, let's just say it's right here at this point, as time goes on, the feather that starts at that dot is just going to flow away from the origin, okay? And similarly, if we look at this part, let's imagine that C2 is equal to 1 and C1 is 0. We just get this curve right here. Again, if lambda 2 is positive, then because e to the lambda 2, or in the first case, e to the lambda 1 of t, these are both going to go to infinity as t goes to infinity when the lambdas are positive, right? When the lambdas are positive, these exponentials blow up as time goes on. So, you know, you could have another initial condition here, but the same thing is going to happen. The feather is just going to go away from the origin. And when both lambdas are positive, it actually doesn't matter what the initial condition is, right? It doesn't matter where the feather is at time 0. When t gets really, really, really big, right, this exponential is blowing up, so is this one. You're going to get a massive vector that's going to be far from the origin. This is called a source. When you have two positive lambdas, you get what is called a source. Okay? The origin is like a source. All of the solution curves radiate out away from the origin in this case. Okay? Another possibility would be if both lambdas are negative. Okay? In that case, you won't be surprised if the lambdas are negative, of course, e to a negative times t, then when t gets bigger, those exponentials actually go towards 0, don't they? Right? Negative exponentials tend towards 0 as time goes on. That means that the exponentials are going to be shrinking the vectors. So as time goes on, notice the direction of the arrows that I'm putting on these curves here, right? They're all coming in towards the origin. This is called a sink. A sink. So when you have one positive and one negative eigenvalue, you get a saddle. When they're both positive, you get a source. And when they're both negative, you get a sink. to decide whether you have a saddle or a source or a sink, you only have to know about the lambdas. You don't have to find the eigenvectors. You don't really need to actually find this solution here. You just need to know whether the lambdas are both positive, both negative, or one of each. Okay? I'm kind of assuming the matrix is non-defective. It's a 2 by 2 matrix. Things can, of course, get more complicated if the eigenvalue is repeated and it's a defective matrix. I'm not going to get into that with you. You don't need to worry about that. Okay? But for a non-defective matrix, you could have 2 lambdas with opposite signs. That's a saddle. They're both positive. That's a source. They're both negative. That's a sink. Or, there's one more thing, which is that the eigenvalues could be a pair of complex numbers. They could be a pair of complex numbers. Now, if you remember, when that happens, of course, you're going to get, e to the at. Then you're going to get cosine of bt plus I times sine of bt. And then times your eigenvector right here, which has a real and imaginary part, right? And then you floy that out. Remember, you just floy that out, and you end up getting, basically you end up getting e to the at. Well, you get, c1 times e to the at times something, and then plus c2 e to the at times something. And the something has to do with sines and cosines of bt, right? I'm not going to write out, the whole general expression here. So sine and cosine, sine or cosine of bt. It's going to look something like that, okay? Well, what's going to actually happen here is the sine and cosine parts are going to oscillate every 2 pi units, essentially. The sine and the cosine are they're periodic, right? And they're attached to these vectors. And the e to the at is what's going to control sort of the growth of the vectors, right? Away from the origin or close to the origin. And so what ends up happening, in fact, maybe what I can do here is, so you essentially get something like this. This is going to be, let me just try this again. I think I can maybe say this a little bit better. So this x of t is, of course, e to the a plus or minus bi t times v, the vector, and the vector is r plus si, right? Remember that? And then, so this just becomes e to the at. You're going to get cosine of bt plus I times the sine of bt, and then it's going to be foiled with this vector right here. Okay? My point is that if you kind of look at the part in brackets, right, as t goes through cycles of, well, it's really bt, going through cycles of period 2 pi, this cosine and sine stuff is just going to repeat itself, right? It's a periodic nature. This is just a constant vector right here. So this whole part in brackets really just is cyclical somehow, right? Every 2 pi units, every time bt runs through 2 pi units, right? This is a vector that kind of runs through a cycle. But it's being multiplied by this e to the at, right? Now, if a is 0, then what's going to happen if we think about the vector? This is a vector, right? Well, it's just going to keep coming back. This is where it starts at t equals 0. Let's say the vector's right there. As time goes on, it's just going to go around 2 pi units or whatever and come back to the same point. And the curve that's being traced out is some kind of a closed loop, right? So imagine if a is 0, there's no exponential part, this vector will keep retracing itself, kind of like the way the hands of a clock just keep coming back to where they were 12 hours ago, right? Or 60 minutes ago or whatever. So that's the idea here, and this is called a circle. This kind of a phase portrait is called a circle, which just means it's not necessarily exactly a circle. It just means that the vector keeps tracing over itself over and over again in a periodic nature, right? Now, what is going to be different about that if the A is not 0? Well, if A is positive, let's imagine that A is positive right here, right? E to the AT. This vector is continuing to trace out the circle as we explained, but it's getting stretched as time goes on. It's being made longer and longer, so that even though its direction keeps coming back to, you know, the same direction that it started at, that vector is going to grow in length. It's going to grow in length. So it might start here, and then here, and then here, and then here. Right? It's getting longer as we go, as time goes on. Now, what's the path? Right? If we look at the tip of this vector, right, it's still kind of in a circle, but it's going outward. The radius is, if you want to call it that, is getting bigger, and this is called a spiral. You can either call it an outward spiral, or sometimes people call it an unstable spiral. Okay, so the idea is that you have a vector here that's periodic, that's just repeating itself, but it's getting stretched longer and longer. So instead of this picture that keeps just repeating itself with the same radius on it, now the radius grows and gets larger and larger as time goes on. Okay? So that would be one possibility. And of course, I bet you know what's going to happen if A is less than 0. Right? Now, if A is negative here, the vector that's in the brackets is going to continue to periodically repeat as before, but it's going to get shrunk smaller and smaller. So, you know, the vector might start here and then like this, and it's going to get smaller and smaller as it keeps going around. You're going to get a spiral. This one is an inward, I'm going to just draw an arrow on this, inward or stable spiral. It's an inward or a stable spiral in that case. Okay? Guys, I'm not going to bother you for exact pictures of these things. And by the way, there's not just one spiral here. Again, if the feather starts out here, well then it's on that spiral, and as time goes on, if this is some sort of a rotating vortex around the origin, right, we have this unstable spiral. The feather will go around in a circle out to infinity. But if the feather started here, well then that's a different spiral, but it's kind of going to do the same thing, right? It's just going to be interwoven with the spiral that's already on there, right? So there's actually not just one spiral here. There's a whole blending of spirals, right, that are all kind of laced around, spinning around the origin here in an unstable or an outward spiral fashion, okay? But whether the spiral is clockwise or counterclockwise, whether it's got a quick outward trend or a gradual one, whether it's actually, you know, very regular and smooth the way I drew it, or whether it's got some bumps in it, things like that I'm not going to ask you for. Very unlikely I would even ask you to draw one of these. Okay, there's just not that much that we can do without a lot more analysis to figure it out. You can put these on computers and get them to draw phase portraits for you anyway. So we're not going to dwell on that aspect of it, but I do want you to know that if your eigenvalues are complex and the real part of the complex number is positive, we're going to get an unstable spiral. Okay? If the real part is negative, we're going to get a stable spiral. And if the real part is 0, we're going to get a circle. So guys, there are 6 things that can happen, right? We can get, you know, we can get with real values of lambda, where lambda 1 and lambda 2 are both greater than 0, we get a source. or they could both be less than 0, in which case we get a sink. Or we could have one positive and one negative eigenvalue, and that is a saddle. So a source, a sink, a saddle, or a circle, an outward spiral, or an inward spiral. And it all just depends on the lambdas. I don't actually have to solve the whole system. I don't have to find the eigenvectors at all. I just have to know what my lambdas are to decide the nature of the phase portrait, which of these 6 things it is. And I think I'd like you to be able to identify those for me. It's not a hard thing, right? If I've told you these 6 different scenarios, all you have to do is find your 2 lambdas. Remember, we're only talking about 2 by 2 systems here. And you'll be able to answer the questions. Okay? I hope that this makes some sense. As always, I'm happy to help. We can talk about it some more if you have questions about it. Let me know, and I'll try to clear them up for you. Thank you guys very much for watching, and I'll see you all again very soon. Thanks.